Alright, hello everyone. It's April 29th. Man, what the hell is with this? It's like weekends is always gonna be hard. Checking existence of edge length limited paths. An undirected graph of n nodes is defined by edge list. Perfect. I denotes an edge between node and node and the distance. Note that there may be multiple edges between two nodes. Multiple edges between two nodes. Given an array query where queries I, P, J, P, Q, and limit, your task is to determine for each query where there is a path between P and Q such that each edge on the path has a distance strictly less than limit. Return a Boolean value answer when answer length is the query length and J value of the answer is true if there is a path for, where answer's length, okay, it's the same, and then J's value is true if there exists a path, otherwise not. So we want to find a path in the graph such that go from P to Q, a path between them such that each edge has a distance strictly less than the limit. Okay, so this is what we have. We have 0 to 1, 1 to 2, 2 to 0, 1 to 0. 1, 2, 3, 1 to 0 have two paths. 1 to 0 have two paths, 2 and 16. And we want to go from 0 to 1, smaller than 2, strictly smaller, right? That's what we are looking for, strictly less than. So we don't have 0 to 2, 5, we have 1. 10 to the 5th. Jeez, man. Okay, this is the path. So we want 0 to 4. 0 to 4. Smaller than 14, that is true. 1 to 4, smaller than 13, that is false. Ooh. What do you think? There are 10 to the 5th edges. Okay. Maybe we need to know the biggest length of the edge. So what you're going to, query 0 to 4, so we need to find all the paths from 0 to 4. Not all the paths, we just need to know the longest distance between two edges, two nodes, okay? The longest. And we definitely need to save some values so we don't have to do it again. Is there anything else? I may have multiple paths, that doesn't really mean anything because all we care about is the smallest if you have multiple paths. So that one is already handled. We just go through the whole edge list. We need to build a graph, right? So adjacency list. So in the adjacency list, we will also include the length. And what we can do is make sure that adjacency list will be another dictionary, which is fine. So we will have to keep the length the smallest if there are multiple, because the larger length doesn't really matter, right? Doesn't really matter. We only care about the smaller one. And then P to Q. Now the thing is, if you go P to Q for the first one, we can of course, DFS it. And can you DFS? I don't know. DFS to find everything? To find everything, like everything? Let's say, and it doesn't even say, is it connected? It's just an undirected graph. It doesn't even say it's connected. So maybe it's not even connected. It could be not even connected. I mean, we can give it a shot. I don't know. True and true. Right? It doesn't even say if it's connected. I mean, what we can do is, I like to use this. I know n is 5. Can we make it not connected? Well, how do we make it not connected? Let's, let's say take 4 out. Okay, if we take 4 out, then we don't do 3 to 4. Let's just do 3 to 2. Yeah, 3 to 2 again. Like this. That should be just false. Oh, it's not necessarily connected. I mean, when you go through the whole thing, right? You say, okay, we start from 0. Oh, I mean, each node is only visited once. Really? Visited once? I mean, for all the nodes that's in, I mean, how do you handle this? If it's a cycle. If it's a cycle, let's say from 1 to 2, right? And then we say if this 2 doesn't exist, okay, let's try one more time. Okay, so let's say the 1 to 0, 16 does not exist. And we want to go from 1 to 2. Okay, let's say we go from 1 to 2, and we want it to be smaller than 5, which exists because 1 to 2 is here. But if you traverse, yeah, this will be true. So when you traverse, right, when you traverse from the start and you go to the next one, I will know if you pick a root, right, and I have all the other nodes that are in this tree, so I shall know the minimum to all of them. But if I do, is it like additive? I don't know. This is right? I'm just drawing some stuff. I don't even know. Okay. 1, 2, 3, 4, 5, and 6. Let's say I'm at 1, right? Now at 1, what I can know is the smallest distance to 2. So 1 to 2, 1 to 3. I know the smallest distance, right? I know these two. But what if I want to know from 1 to, let's say, 5, right? From 1 to 5. Can I say, well, I mean, I need to know a path from 1 to 5. There are many paths from 1 to 5, okay? There are many paths from 1 to 5. But I know the smallest is here, smallest, okay? Then we are at 2 and at 3. And the question is, how do we get to 5? Well, no, there are many paths to go to 5. But we want to find the smallest. Is this like, it's not, it doesn't really mean the smallest. We just need to know if there exists a path, right, that's smaller than. So like each path is the smallest right now. Each path is smallest right now. And to get a 5, I mean, I'm not sure, but I mean, there's also the question if, okay, maybe the first question is we need to know if they're even connected in the first place. Now that we can use DFS, right? We can DFS and put them together, okay? DFS and put them together. So I will know which nodes are together, right? Which nodes are together. I can use DFS, I can use union find, doesn't really matter. So what I need to know is who they belong to. I mean, I can DFS and everyone will have the same parent. That's fine, right? That's fine. So I can check P and Q, right? If they have the same parent, at least we know that there is a path in between them. Otherwise, no. Okay, that's the first, right? So first step, we need to find all the cliques, right? All the connected components and mark, right? Mark the group, right, of each node that it belongs to. So that's the first. So now we know if P and Q does not belong, that's going to be false. If they belong, so in a second, we say if P and Q belong, right, to the same group, then there must be a path. There must be at least one path, right? At least one path between them. Now the question is whether this path, whether this edge, at least one edge, yeah, one path, this is a path. So now what we want to know is if there is an edge in this path that is bigger than the requirement. I mean, we will be able to know the length of all the edges in the group. We can do that. We can know the length of all the edges, right? Have all these edges. So let's say we have also a collection of edges, okay? Also, we have a collection of edges, collection of edges in each group, okay? Then we will know which edges are larger. Which edges are larger? Okay. Now the question is, are these edges involved in the path? Man, I don't know, this feels just convoluted. Can we just traverse it? I mean, you can because of the restrictions. The size is just too big. You can't like just traverse given any pairs, right? You give any pair, you try to traverse them. That's not possible. But there gotta be a way. There gotta be a way out. I mean, we will know the largest edge. So if the given edge is larger than the largest edge, that's also solved. But it's also a trivial case. The difficult case is the given edge is, not larger. So it's kind of, or if it's smaller than everybody, and that's also going to be false, right? But if it's in the middle, how do you handle? And remember, the thing is, like, if you have, let's say I have 1, 2, 3, and this like will have a giant value, and these will have small values, right? And this will have a giant value. Then you say from 1 to 3, you can always go around, right? Because it doesn't really matter how long. All it needs is to have a path. There exists a path. If there exists a path, each edge is strictly smaller. What if I traverse it once? What type of information would I get if I traverse it once? Or let's say, if I know from 1, let's say from 1 to some node, right? 1 to 2, that's good. And then from 2 to 3, that's good. Then we know from 1 to 3 is also good because 2 is in the middle, right? Yeah. So, and we know all the nodes are connected. All the nodes are connected. All the nodes are connected. This is a clique, right? And there might be redundant edges. And there definitely will be some edges good and some edges bad. Well, how do you know some edges are bad? That's the thing. You don't know if some edges are bad. Or the question is, you know all the edges, right? So if I remove some edges, right? You know, some edges are good, some edges are bad. So what if I remove some edges? If I remove, yeah, basically that's the question, right? If you're giving me a graph, okay? You're given a graph, and we also know all its edges, and their weight, no, their length. Now we say remove edges that are too long. If we remove the edges that are too long, can we still go from P to Q, right? Can we still go from P to Q using the remaining edges? Can we solve this problem? But man, the query length is also large. Dear Lord. I feel like I'm not on the right path. Can we follow this? We have something. We have some graph. Doesn't really matter, some graph. And we say if we remove some edges, how do you know if you remove an edge, then it will be bad? It will not. Well, we need to know what edges are in each one, right? I mean, that will be in the graph, right? I know who's in the graph. But you know which edges are in it. Do you know that? I do not. And possibly, I don't know, this all take a long time. I mean, we can prepare edge list, okay, for each group. Okay, let's just say we have all the edge lists for this one group, and we can sort based on the edge length. Okay, and of course, duplicate edges are removed. We only keep the smaller one. Okay, that's fine. And then we sort them based on the edge length. Now you're giving me a target limit. Okay, so we can binary search to know which ones are removed. Okay, so you can see which ones are removed. You can see the nodes that are removed. All right, so you will see the nodes that are removed. Okay, so you know those edges no longer exist. So if the target is one of those removed, and that one has only one edge, and then you got removed, and that one become unreachable, right? So the question is, if you remove an edge, will it make, right? Will it make? But if you think about the runtime, we have to go through the query one by one, okay? And for each one, we have to binary search. Right? For each one, we have to binary search. And we have to go through all the one that are removed. All the one that are removed. But how do you know if it becomes... I mean, even if it's not connected, that's fine. If the target, right? If the target is within the target, wow. This one I actually have no clue. Yeah, I think it's just you cannot pre-compute, let's say, the smallest path to everything. You cannot say like 1 to 2, 1 to 3, 1 to 4, 1 to 5. Right? I feel like it's gonna time out. And like how do you even do that? Can you traverse it once? I mean, all we need to know is the smallest path. Smallest, no, the biggest edge, right? The biggest edge. And I still think we should traverse it. But how? We start from a position and then we keep going, right? Then we say from this to this, what's the smallest? And then what? And then from this, we'll go to everybody else, right? Except the one that you have visited before. Okay. And you go... I don't know, man. Yeah, we want to find the largest. Not really the largest, it's still the smallest from one node to everybody else, right? No, it's the largest. The largest, smallest, okay? The largest, the smallest. So if we start from a node, right, we go to the second node. So we know, and then from this second node, I can go to everybody else because they're all connected. And then from the first node, I can go to everybody else. I can't even solve this, the basic. Like if I starting from here, if I start from this, I say, find me the biggest, smallest edge. Find me the smallest edge going to this node. Can we even do that? We start from here. Well, the first step, we go here. We know that we need to know the smallest from this going to here, and from this going to here. Right? And then we go from here, and then we, so from smallest from this go to this, and we'll go here. So that's the smallest from this to go to here. But the smallest from this to go here is not just this, right? When you are here, you want to find the smallest going to here. It could be like, I don't know. I mean for this one, yeah, that's only one way, because there's only one way. No other ways can go here. But if there are another way, yeah, you do try another way. Or should we say, like if you're given this, like in this problem, right? We have 2, 1, 0, 4, 8. We pick 2 because 16 is useless. And when you have this, can we just eliminate this? Because if we want to keep the graph connected, we don't need this. And this is huge, right? If we don't need this, then the smallest path from 1 to 0 is 2. From 1 to 2 is 4. From 0 to 2 is also 4. Right? What if our goal is given a graph, right? We want to remove as many edges as possible. Okay? We want to remove as many edges as possible, and all the big edges are removed. So we want, how about we turn the problem into this? Okay, given a connected graph, we want to remove edges, right, large length without, but then sometimes I don't know, because he's asking from, yeah, I mean, that's the same as what we're saying, right? You just need to remove the edges. And is the graph still connected after you remove the edges? That's hard to say. But we can do this first, right? Right, without compromising on the connectedness. Is this possible? Because we're just removing the redundant edges, right? The edges are redundant. Well, I mean, I don't know. What do you think? How will we know if some edges are redundant? Yeah, how do we know if some edges are redundant? Well, the edge is redundant if we have a cycle. But even if we have a cycle, it's hard to tell which one is redundant. Or we can go edge by edge, right? And how do we tell if you remove an edge? Right, you have a graph. How do you tell if I remove this edge? How do you know it's no longer connected? Like something is getting out. How do you know? Well, I mean, in degrees, right? If a node has 1 in degree, then you remove the edge associated with it. Then it has 0 in degree. Then that one becomes not connected. That one gets out. In degrees. So each node, 2, 3, okay, 4, 5, 6. The degrees, so 1 has 2, 2 has 2, 3 has 4, 4 has 1, 5 has 2, and 6 has 1. Okay? So these are degrees. If the degrees drop to 0, then this node is out. So if I have all the edges, all right, sorted, I have an array with the edges, okay, 1, 2, some value, 1, 3, some value, doesn't matter. And a binary search, right? And then I know something. These are the removed ones. So I go through the removed ones one by one, and once I go through them, every time I had it, I will reduce their thing, right? Reduce their thing. And after reduce at the end, we check if the node is still reachable. Okay, that makes more sense to me. That makes more sense to me. Right? We give an edge, we remove it, which means the degrees of the node drop. And we know the original graph is connected, right? So if your degree drops and it's still not 0, that means there's still a path going to you. So you're still okay. That is not true. That is not true. If I drop 3 to 5, like this one's good. If I drop 3 to 5, I say 3 will have 3 edge, 5 will have 1 edge. But then if I want to do 1 to 6 or 1 to 4, then that's no, that's not how it works. Because this is a critical, right? This is a critical edge. Now we also need to find critical edges. No clue. Give me some hint. Union find. That's all right. That's it? That's all you give me? All the queries are given in advance. Is there no way you can reorder the query to avoid repeat? That is an interesting thought. That is actually an interesting thought. I didn't think about this. I didn't think about from the perspective of queries. I guess is the limit. Right? If you think about it, the limit, I mean, higher limit, definitely. A lower limit, right? If we go with a lower limit, okay? We go with a lower limit. And yeah, we go with a lower limit, then we try it. Perfect. We try it with a lower limit. And we say it succeeds. Now, if a lower limit succeeds, then we go for a higher limit. If they're inside, I'm going to say if they're inside the same group, then they will succeed as well. But then I realize, nah, that's probably not the way. Yeah, the problem is about repeated computation, because you are computing it repeatedly, but we want to reduce the repeated computation, which means if we can have a query that, like in, that's actually not quite right. Like, would you gain anything by taking a small query first? 0 to 1 is 2. We got a false. That just means everything is larger than 2. Well, something is larger than 2. That doesn't make any, that doesn't help. Unless if it's, I don't know, 0 to 1, 0 to 2. I mean, technically, if I can let's say, sort the queries, starting and end, okay? We find the most frequent starts. So 0 to 1. Okay, so we have 0 to 1. Then we have 1 to 2. 0 to 2. I have 0 to 3, 0 to 4. And I have 1 to 3, 1 to 4. What? Then you just start from 0. Right? Then you go to if you have the same start, right, and go to different positions, then you can run one traversal for all of them. What if they're all different? What if they're all different? From 0 to 1. Yeah, we can align them together. If we have the same starts, then we can just go do a traverse for all of them. But then the traverse itself is kind of tricky. Dijkstra? I mean, we just need to go to the destination, right? So the next is this or this. So I say, okay, I'll pick this. Yeah, that seems like Dijkstra. And we want to pick the smallest that we have, right? So the next node is this. Then we will always go for the smaller one. And from this, we go for the next. And if it's smaller, we update the path. Right? We update the path to be smaller. Right, we update the path to be smaller, okay. So the path to this can be, yeah, we have the current maximum, okay. And then we go to the next one. We can find the current maximum. If it's smaller, then that's the current maximum. And we also go that's one node to every other nodes. Okay, one node to every other nodes. What if we have, because as we're doing this, can we also record? Well, I mean, from this node. Yeah, what if there's like no repeats? The node doesn't have repeat. Or we can highlight the nodes that need to learn. Let's say we know certain nodes. Okay, we learn certain nodes, and we say we can highlight them. So those are the nodes of interest. Then we want to know, and they're all connected. I want to know this to this. And then we go through some other nodes. Yeah, that's just the thing. We go through some other nodes as well. Or we go from large. But still, that doesn't make any sense, right? Let's say we go from large, the largest distance, okay? The largest limit. And if the largest limit works, we go for a little bit smaller, okay? Until we hit a limit where it does not work. And we know it's a connected graph, right? But still, if it does not work, that doesn't mean other thing doesn't work. Connected graph just means there definitely is a path. And I actually don't have a good idea. I have an idea how to group the connected components together, but after connected components together, like the traverse part is still eluding me. Like, I don't know how to traverse them. Maybe I don't know. And BFS will help. We go from 1. We go to 2, 3. And from 2, we don't go back to 1, we go to 3. Okay, you start from 1. And you end at 2 and 3, right? You end at 2 and 3. So 1, you go to 2 and 3. And you know the distance. So I say from 1 to 2, right? I have the largest to smallest distance. Okay, I have a distance from 1 to 3. I have a distance. Now from 2, 1's visited, so I don't go back to 1. I go to 3. And from 3, I can go to 2. I can go to 5. I can go to 6. So I land in 3. I say I have 2 and 3, right? The current 2 and 3. 3 go to 2, right? I have 2 and 3. But how do I know from 1 to 3? If it doesn't make any sense, then I have 6, 3 to 6. I mean, I know this already. I don't even know, like, say 1 to 5. What's the shortest from 1 to 5? How do I even get there? I go start from 1, right? And then to the next level. My next level is 2, 3. So I know the current smallest, min, right? Go to 2 and 3. And from 2 and 3, now 3 will go to 5. And 2 will go to 3. So the next level is going to be 3 from 2 perspective, right? And 3 is going to 5. 3 is going to 6. So I know going to 5. Yeah, even let's say we can do it. Then we just know from one point to the other point. What if the next question is from 3 to 6? Yeah, this feels Dijkstra. This feels Dijkstra to me. To find the, not the shortest path, but the edges, right? The smallest edges that can go to another node. Yeah, I think we can use Dijkstra for that. Yeah, we always go to the smallest, and then as we go along the path, we'll record the longest, right? The current longest. And if it was on one path, then we swap to that, then we compare, then we go for this, right? And then we go for the next, and then boom, we hit. So we have the value. But we already did the computation, right? We did the computation. So I want to save whatever we had. How do we save whatever we had? It's like we go from 1, right? We traverse, we go from 1, and we can go to everybody. As we go into everybody, can we keep recording? No, there's no hope. No hope. DSU. How would you use DSU for this? Union find. Union find. Huh? Something with union and find. Okay. It's not working. Union find. How does union find help? How would union find help? So we know 1 and 2 union. The weight is 4. Okay. 2 and 0 union. The weight is 8. Now because they union together, right? 1 has its parent, 2 has its parent, and now 2 and 0 union, so 1 and 0 has the same. But 1 and 0, if I do go 1 to 0, and of course at the end 1 and 0 union, and the weight is 2. So some change needs to be made in the DSU code when you union them together. When you union them together, can we find the I'll say is the longest path or shortest path? The shortest, right? When you union something. Okay, how does the union find work? So if 1 and 2, so if I have a parent, okay, so parent will start as 0, 1, 2. Now 1 and 2 union, and their parents are different. And usually we also have a rank, right? And the rank will start with 0. Now 1 and 2 are different, so they want to, the parents are different, but the weights are the same. So we want, let's just say we go to 1. So the parent turns into 1 and 1, right? 1 and 1, that's when the union. And then 2 and 0, right? 2 and 0, and then of course, so 1 gets a higher rank, right? 1 gets a higher rank. And then 2 and 0 union together. Doesn't matter, we can say we choose 2. Because that parent is a 1, parent is a 0. And 1 has higher. So that's how the parent become 1, 1, 1. And that would be 0, 1, 0. And then we union 1 and 0, and that's fine. So the thing we didn't use is this weight. Right? And how do we use this weight? I guess that's what union find is trying to do. We also have to use this weight. And what we want is the query. Right? We query these two. Of course, they belong to different parents, and then there's no good. But if they belong to the same parent, how do we know that? Like, how to represent this relationship between them? Like when I say, if I need to find 1 to 0, right? The weight is not 8, but 2. Because if I find 1, find 0, we know they belong to the same. But there's no information about the weight. No way. Okay. The same resolution will be the form of breadth for search. Yeah, we know this is not gonna work. Yeah, you can DFS however you want. Another way to solve is to create connected components using only edges with weights less than the limited specified in a query. If both the starting and end nodes are in the same component, it means there is a path between them that use only edges. Okay. What we're saying is, you give me a limit. I choose the node, I choose the edges with smaller than this, and I build a graph. Okay, so what you're saying is, I go from the smallest limit. I go from the smallest limit, right? And I pick the edges that only satisfy the smallest limit, and we'll build a graph out of it. Then we check if these two. Oh, I think I know. We will sort queries based on the edge, based on the limit, and we'll build only use the edges. Holy crap. I think I have encountered this before, this type of thinking before. Man, that is correct. We'll get all the edges that's smaller than the limit. We use them, build a graph, right, to check if they are in it. If they're not in it, that's bad. And then we keep adding. Oh, bravo, bravo. Well, yeah, it happens. It's not always successful, but oh. Hey, that is a good question. Actually, I want to see if somebody has answered. What if we don't have them? Minimum spanning tree. I have no clue what this is. I have heard of this, prims, maybe cross-call, because I took some graph class. But man, I'm not able to remember. Minimum spanning tree. I mean, I guess it doesn't matter. Right? Oh, it does matter. No, I think it's fine. You just build a tree up. Oh, but then you don't know, because you have to go from small to large. Then you just need to traverse. This is too advanced. This is too advanced. Alright, let's just finish this and call it a day. You shall be able to know this, man. It's not the first time. It's not the first time you do this. I don't know. I think I've done this before. Seriously. But I was not able to solve it. All right. Key lambda tuple 2 and queries dot sort. Right. Then we'll find everything that's smaller. So we go from the first, and then we go from this, right? And DSU will equal to DSU n. Okay. Then we say we go from each query, right? For PQ lim in queries. Then we need to know the I is 0. While this is smaller, then we put them together, right? While edge lists I okay. While I is smaller than len edge list, and this one is smaller than lim, then DSU.union edge list I 0, edge list I, well, that should be 2, right? If it's smaller, then we do this. If it's larger, then we stop, right? I plus equal 1. And then we just, we need the answer. Res.append DSU.find P is equal to DSU.find Q. Right? That's what we done. Go back up. And then we try to have a new limit. Then I just keep going, keep adding more and more edges until at the end I is, and then we just keep doing this. Then we return res. Dear Lord, solution is so simple. I mean, you know what? I feel like this should be right, so I don't even want to test it. It is sorting from small to large, and you build it up. Is this right? What? Oh, that's shocking. False, true, false, true, false. Expected true and false. Oh! I know. I hate it. Sort SE sorted. Sorted. For gosh. UV, D, and I. And enumerate this. Okay, key equals to, that's still fine. U, V, D, I. We have to go, and then key equals to top 0 and 2. Yeah, that's fine. So we do this. Sorted edges, sorted queue, sorted queries. Now queries is going to be PQ. I can call it L. Okay, PQ L. Okay. Then we will do SE. Okay, so that we also need I. O. We have I already. J. Wait. Is a query, right? Yeah, it's query. So that's fine. So it's the query, right? So query, so we have a J. And answer shall be 0. Is it true times len queries? Oh, then edges doesn't really matter. Yeah, we don't really care about edges. Dirt. We don't care about the edges. Edges is fine. Queries needs to be treated specially. I might as well just do this one here, right? We don't do it here. We do this, right? We use I already. Let's use K. Right, for K, enumerate, then we'll sort based on this, based on that limit, and then we get out. And we do blah blah blah. Then we say res J. Well, we can do none equal to this. All right, how about this? Slightly more complicated. Must be parenthesized. Did you not parenthesize? First of all, sorted. No, you did not parenthesize it. List out of range. That is strange. Oh, this will be queries. Dude. Queries. Small to large. Build it up. Nah. Tough one. But once you know the trick, it's actually not that bad. Yeah, we count this as a fail. Let's put this one into the nightmare. Well, once the secret sauce is revealed, it's not that difficult. This is not the first time that I have seen this thought process. All right, we start. We to know whether there is a path between two nodes. We create the graph using the edges allowed at the moment, then with union find, it is very easy, right, to check whether the target nodes are connected. We slowly build up the graph, right, with ever larger edges, but each time the edges are always within the limit, which means for whatever graph built, all the edges are okay to use. Yeah, this is the main thing. Well, O1 log n, well actually O edges log edges plus queries log query, because we have these two, and then times plus, this is actually plus edges and a total thing, because you also need to multiply it by, so each edge, so E times union. That's how I would do it. What's the runtime? E log E, and then what's n? Oh, DSU is n. What considered to be O1. So this is also edges. Yeah, we forgot the n. Yeah, we forgot the n. We have to use n. And then edges plus q. It is edge plus q, yeah. Edges plus q, that's correct. Good question, very good question. All right, well, let me savor this a little bit. All right, that'll be it for today. I'll see you guys tomorrow. Adios.